Real quick, orbits, not obits, have a lot to do with actions. They're defined really in terms of the action. So what I'm going to, at least the way I'm looking at them, what's that? It's a tape. What's going
No,
on?
your tape is fine. The focus is fighting me. I'm sorry to interrupt.
Yeah, it's done that on the earlier tapes too.
It's going in and out.
I got it. It's cool.
Okay.
Carry on.
Orbits. The orbits are going to be basically sets. If I take some vector v and I apply g to it, so I started out with a vector v, and I apply g to it. Let's say g is a rotation. G can be an element of any group, so let's let it be in the regular orthogonal group in 3 dimensions. Then maybe I'm going to rotate it, and so that it ends up later here. This is on a sort of cone. Okay, so I rotate it about the z-axis. Okay, then I end up with if I look at that continuously, there's a continuous group of transformations that rotate about the z-axis. So v moves to here, then to here, then to here. Later on it's there, later on it's going to be over here, later on it's over here. And it spells out a cone before long. See that? Okay, well, we're not looking at the actual length of the vector. We just care about the position in R3. So you really just get this circle at the top of the cone. Okay, so an orbit, this is an example of an orbit. An orbit is all of the, it's GV, so the orbit of V, I should say. It's given V in your vector space. What's a good, how do we usually denote orbits, Catherine? I've got specialized notation, but I don't have general notation. For like an orbit of V, I don't want to call it O of V, because that's too reminiscent of the orthogonal group.
I've seen it like G of V.
G of V. I'll do that. G. Yeah, that's the best way. G of V like this. Okay, that's going to be. And did they use the parentheses or did they just write GV? I think you wrote GV.
Yeah.
Yeah. Okay, so GV. That's what you did. Is going to be G times V. Such that G is in G. That's it. So you're given a particular vector, like we started out with just some vector, and then you look at all of the group elements applied to that. You range over the whole group, and you look, and that gives you a collection of vectors. So what we got was this circle. Does that sort of sit well with you? Okay.
Well, you range over the whole set of vectors.
Or you're ranging over the whole group.
Ranging over the whole group. All
Because
right.
this is such that G is in G, so the G is sort of arbitrary. It goes over all of G. I'm given a V,
Right.
and then I apply every group element in the entire group to V, and that gives me
Okay.
sort of
I see.
some shape. So what I've done is, actually this is not every group element, right? This is, if I start with V right here, I've only applied rotations about the z-axis. Now I start applying rotations about the x and y-axis, and what I'll get here is a sphere. You can just think of starting with V and you rotate it any direction you want.
Right.
It's going to spell out the entire sphere of length norm V. Okay, the length of that vector V. So you actually get an entire sphere. Okay. And so if I look at the orbits of just O3, let's do SO3 because we don't know. Orbits of SO3, those are all the rotations, then you just get spheres. Okay, so, and if I look at all of the orbits, they're going to be spheres of different radii. So it's like these concentric spheres that build out. Like that's all the orbits. And one sphere is an orbit of all the vectors that are whose lengths have the same radius as that sphere. Okay, so that's sort of should be a good geometric picture of this special orthogonal group. And we're running a little past 10 o'clock. We got started late, so we need to take off. It's fine. All right, so this we're going to go back into just a little bit of physics, and then I'll end it. All right. Oh, I didn't talk about that one. Let's talk about one more little map. I'm going to give you, let's see, there is another homomorphism. I'm going to call, we know that the first one was the determinant, right? We talked about the determinant for a little while. There's another homomorphism, and it's going to be this one. Call it psi from, oh, by the way, the determinant homomorphism from 013, actually, you can show that if you're in the generalized orthogonal group, remember when you were in the orthogonal group, the regular old orthogonal group, but it should always be S. No, sorry, that's right, that's good to know. When you were in the orthogonal group, you had either determinant +1 or -1. We showed that. It's the same if you're in the general orthogonal group. So this doesn't just go to all real numbers, it only goes to 2 elements, in fact. So if you're picking the subgroup of 013 that goes to +1, you're really picking half of the group, because the other half goes to -1. There are only 2 places for the elements of the orthogonal group to go, plus or -1. Okay, there's another homomorphism psi from 013 to the group. This is, by the way, plus or -1 is a group, okay, under multiplication. So we're going to treat it as such. It's isomorphic to Z2, because the integer is mod 2. Okay. This one is going to be given by psi of A equals, I'm going to write it like this, A, alright, so this is one. Oops, sorry. It's not. I want the sign. Okay, what that means is A is a bunch of matrices, right? So, do I have many? I've erased all the matrices. But you've got these cinches and coches and stuff like that. All right, if you look in the upper left-hand corner, this is where your A00 is. This is my matrix. A is going to be in the orthogonal group. This is actually the, okay, I'll call it the Lorentz group. Your upper left-hand entry is A00. So if you just look at the sign of that entry, that's actually another homomorphism. Is this sign positive or is this negative? Okay, this sign is either going to be positive or negative, and so it's a homomorphism into plus or minus 1. All right. Now, here's where the physics comes in. Let's look at the kernel of psi. So the kernel is whenever the sign is 1, positive 1. Okay. Kernel of psi is going to be given a name. It's going to be called O, or this is a symbol, O with a little up arrow, 13. It's called the orthochronous Lorentz group. Called the orthochronous Lorentz group. Orthochronous. You're going to guess, well, chrono means time. Okay, we're dealing with the time coordinate.
Right.
What these transformations do is preserve time order. Okay,